Hey guys, this is the lecture recording for Module 8 over excitable cells. As we go through this lecture, just like the last time we had a recorded lecture, I'm going to prompt you to pause the video to answer in-class questions just like we would in class. Take your time. These are available on Top Hat in the in-class question or in-class activity folder. So those should be available to you as we go through. Let's get started. First, let's talk a little bit about what an excitable cell is. Excitability is just the ability of a cell to either send or receive electrical signals across a plasma membrane, right? Just like we saw in the skeletal muscle cell and the neuromuscular junction, we were able to initiate an electrical signal inside of the muscle cell based on a chemical that was sent to the muscle cell from the associated motor neuron. The signals that we're talking about, these electrical signals, are generated by utilizing concentration gradients. Think about the neuromuscular junction when we first bind acetylcholine to the receptor. That's going to open up those sodium and potassium ligand-gated ion channels. And that movement of sodium and potassium across the membrane that is caused by the concentration gradients of those ions is what starts, right, the signal. Any cell that has an electrical potential or has like a difference across the membrane in concentration of charged ions is said to be polarized, and we'll talk more about what that means later. But for now, just know that that is a term that we will be talking about as we go forward. We have here a table with some typical ion concentrations that are both inside and outside of a neuron. Potassium, on the inside we tend to have 140 millimolar. Millimolar is just a unit for concentration of especially things like ions or vitamins, minerals that are really small. But we have 140 millimoles of potassium on the inside of the cell, and only 5 millimoles on the outside of the cell. So if left to its own devices, right, potassium would flow from an area of high concentration on the inside of the cell to the area of low concentration to the outside of the cell. Remember when we talked in module, 1 or 2, when we talked about concentration gradients and we had those videos of ink spreading in water, right? We're looking at the same basic principle here, high to low concentration in this case. For sodium, it's a little bit backwards from that, right? We tend to have 15 millimoles inside of the cell and 150 on the outside. And so sodium, if left to its own devices, is going to flow inside of the cell from an area of high concentration on the outside to low concentration on the inside. Now remember that these two gradients are generated by the sodium-potassium pump. And so these are kind of artificially generated, except that the sodium-potassium pump is completely natural and important. The movement of these down their concentration gradient is secondary active transport because we had to use ATP to get them to these gradients in the first place. Moving on to chloride ions, we've got a chlorine, negatively charged chlorine ion here. So chloride, there's generally 10 millimoles on the inside and 120 on the outside. So again, just like sodium, chloride ions are going to move inside the cell, which we have seen, right? We know that, we haven't seen that with chloride, goodness gracious, we've seen it with calcium. I got a little ahead of myself. But with calcium, we have 0.008 of a millimole on the inside and 5 millimoles on the outside. And so again, we're going to see movement inside of the cell, which we have seen here with calcium, right? When the signal comes down the axon to the neuromuscular junction, right, in the axon terminal, it opens up those voltage-gated ion channels that allow calcium to move freely down its concentration gradient, and it moves into the cell, right? We've seen that, and then those vesicles, those synaptic vesicles are going to be released. Their contents exocytosed, right? We saw that from that result. So that is why calcium will flow into the cells, because we have, right, this concentration gradient. To calculate a concentration gradient, really, it's a basic, very simple equation wherein we take the concentration anytime you see brackets around an ion. So if I were to write like this, the bracket means concentration. So anytime you see brackets with an ion, it's just saying the concentration of that ion. So the concentration of an ion on the inside of the cell minus the concentration of the ion on the outside of the cell. So we're doing just the difference between the inside and the outside of the cell, and that is going to tell you the gradient. So let's do an example here. We start with sodium. So let's take our normal numbers, right? Those kind of averages that we saw earlier. On the inside of the cell, sodium, the concentration is about 150 millimolar. And on the outside, it's 15 millimolar, right? So we know just by thinking about this, if it's going to move from high to low concentration, that it's going to go from the inside of the cell, or, hang on. Okay, I fixed it. Turns out it was just a little issue on my part. I just completely flipped the out and the in. So, anyhow, moving right along, starting over with this slide, my bad. Our example here, sodium on the outside of the cell, generally that's about 150 millimolar, and then on the inside about 15 millimolar, right? That's what we saw right here. So 15 on the inside, 150 on the outside. And by the way, while I'm thinking about it, this gradient, we're really, honestly, any difference is fine. So if like the concentration on the inside is the bigger number, do in minus out. If the outside is the bigger number, do out minus in, right? You don't want to have to deal with negatives that way. We're just looking for the difference between them, really. So back to our example, our gradient, we have 150 millimolars minus 15 millimole, right? Millimolar, that's a difference of 135 millimolar. And so we're going to see movement of the sodium from areas of high concentration to areas of low concentration, right? That's what this means. And so that's the difference. This number doesn't give us a lot of information by itself, but what it does tell us is how these numbers, how the gradient is affected when these numbers change. So let's say that the internal sodium concentration increases, okay? So instead of starting at 15 millimolar, right, like we have here, here's what we had before. We had 15 millimolar on the inside and 150 on the outside. Now we have 50 on the inside and 150 on the outside. So now our new math, we have 150 minus 50. Now it's at 100 millimolar instead of 135. So the gradient decreases. So we go from, right, 15 on the inside, where we have lots of sodium moving in, to 50. Well, now we have sodium moving in at a slower rate because the gradient is not nearly as steep. We could also see a decrease, right, on the inside of the cell. So we start again with our 15 millimolar on the inside. This is kind of our standard, and then we can decrease that to 5, right, from 15 to 5 millimolar. So now our new gradient, we start with 150 on the outside, 5 millimolar on the inside. This is a difference of 145 millimolar. So here the difference is 135 millimolar, but that gradient is going to increase. It's going to get steeper because the difference is much bigger. And so that gradient will increase. We'll see a faster rate of moving, of sodium ions moving throughout, from the outside of the cell to the inside. So here's our first in-class question. Go ahead and I would suggest taking a couple of seconds to answer this question. So given the following information, what is the concentration gradient of ion A? So ion A, the concentration on the inside is 250 millimolars, and on the outside it's 50 millimolars. So is that a difference of 200 millimoles, 300 millimoles, 250 millimoles, or 50 millimoles? So it is up to you guys. Go ahead and take a couple of seconds and answer that question, and pause the video until you are finished with the question now. I hope that you took a couple of seconds and answered that question. The correct answer is A, right? So let's do the math together. We start with 250, right? That's the concentration on the inside, minus 50. That's the concentration on the outside. and we're left with 200 millimolar. That is our gradient. We've seen these before, but just so we can kind of refresh our memory, we have ion channels that are going to help us propagate signals, right? And their job is to transport ions across a membrane, so they're not having to just diffuse on their own. It goes a little bit faster when they have this channel open and available to them. We have channels and we have pumps. Pumps, of course, are only going to allow passive or secondary active transport, and these ion channels and pumps all exhibit specificity, meaning that they're hyperspecific as to what kind of ion they can let through. So for example, let's start with a voltage-gated ion channel, right? When the voltage changes near the ion channel, it's going to open that gate and allow one type of ion to move through, maybe sodium, maybe potassium, maybe calcium, right? With a ligand-gated ion channel, just like our acetylcholine receptors in the neuromuscular junction, when we have a chemical or a ligand that binds, right, to this receptor, it's going to open that gate and allow one kind of ion through. So like a sodium channel, for example, would not admit potassium. Now remember that once these are open, this is passive, right? This is passive transport down the concentration gradient. And so influx or efflux, it could be out of a cell, right, of an ion increases as the gradient increases, and it decreases as the gradient decreases, right? This is stuff that we've seen before, should be review. Now, a key point of note here, in a healthy individual, relative concentrations between like the inside and the outside of a cell for an ion are generally constant. The ions that actually do move, because remember, they're always moving, represent only a teeny little fraction of all of the molecules that are present in the interstitial fluid, which is the fluid in between the cells of the tissues, and the cytoplasm. So for example, sodium is always going to be 10 times more concentrated on the outside of the cell than the inside, right? It stays fairly constant. In unhealthy individuals, we can see vast changes in those comparative concentration gradients. But generally, these are going to be homeostatically controlled and fairly constant. So we have another question here. Go ahead and take a couple of seconds to answer this. True or false, the concentration gradients for any one ion generally stay constant. So go ahead and pause this and to answer it now. All right. So, of course, if you were to have rewound right back to here, we would see that the answer, of course, is true, that the concentration ions generally stay constant. Now let's talk for a hot second about ions. Like, what are they? We've talked about them quite a bit, but let's just take a second to talk about what they are and how they affect each other. Ions are what we call charged particles. They can either be positively charged or negatively charged, and that just has to do with like the number of protons and electrons that they have, blah, 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 yada, yada. This is not chemistry class. I'm not expecting you guys to know why they're positively or negatively charged, but just know that they do carry charge. Sometimes they even carry like multiple charges, right? You can have a 2+ like calcium, that sort of thing. If ions are distributed unevenly across a membrane, so there are maybe, say there are 15 positively charged sodiums on the inside of the cell and 30 on the outside of the cell, okay? That means that on the outside of the cell you're going to have, 30 positive charges, and on the inside it's only 15. So that's an uneven distribution of charge as well as of ions. So that's going to net like a negative 15 difference, right, between 30 and 15. If the ions are permeable, right, so if the membrane is permeable to those ions and they're being transported across the membrane, then the charge distribution is also going to change. So, for example, if we have sodium, right, 30 on the outside, 15 on the inside of the cell, sodium is somewhat permeable. It does kind of leak back and forth. We start off, let's just write this out, 30 and 15, there's the line of the cell here. We start off with like a change in 15, but we're going to see sodium kind of leaking back into the cell. So instead of having 15, probably going to end up with like 20, and then we'll have 25 here. And now the difference is only 5, right? And we would see this until we have equal numbers of ions on either side of the membrane, until we've reached what we call equilibrium. But it's not just concentration gradients that affect the way that ions move. Because we have two different types of ions, they affect each other differently. So we start here with a negatively charged ion. We call these anions. We also have positively charged ions. These are cations. And if you guys are chemistry buffs, you know that these two ions, anions and cations, tend to like to form compounds together, which is true. Some ions really do like to form compounds with other ions. Take, for example, a sodium ion and a chloride ion. We have a cation in sodium and an anion in chlorine. And so when we put these together, they form a lovely compound that we like to eat called salt, right? So for those of you who are familiar with those concepts, that might help you out here. But for those of you who are not, don't stress about it. We're not going to have to know it. This is not chemistry class. Just know that we've got anions and cations, and they have interesting relationships with each other. And I have no idea why this is like this. These are backwards. I'm going to fix it. Hang on. Okay, that's much better. Sorry about that. So before we had these arrows here and those arrows, and they were backwards. This is what you get for rushing things, Callista. All right. Moving right along. So we have an anion, and a cation here. Cation positively charged, something like sodium or potassium. Anion negatively charged, like chloride. And these two are going to attract each other. Opposites attract. They're going to pull each other close. However, if we have two anions, these are the same, and they don't want to come together to make a compound. They don't want to attract each other. In fact, they repel each other. If you've ever held a magnet and tried to force it together and not been able to because it was just pushing itself away, know that that is because of the electrostatic forces in that magnet, right? You can't put two north poles of a magnet together, and you can't put two south poles of a magnet together. Just like you cannot force two anions or two cations together. They repel each other. And so these two ions are going to push each other away, and these two ions are going to push each other away. But if you put a north pole and a south pole of a magnet together, they're going to attract. They're going to magnetize, right? They're going to stick together. And same with an anion and a cation. We've got opposites attract and like ions repel each other. This is a good summary of electrostatic forces. And those are going to help us figure out exactly where these ions are going to move, which is important because we're talking about excitable cells. We're talking about the ability of cells to use those ions and the movement of those ions to generate a signal, right, a message. And one of the kind of key things that we need to understand before we do this is something called membrane potential. So membrane potential is a form of potential energy. Remember we talked about potential versus kinetic energy. If I'm holding a ball above my head, I'm not moving the ball, I'm not like releasing the ball, it's sitting there. But the ball has potential energy put there by my arm, right, which I've raised over my head. If I drop the ball, right, I'm still holding energy in my arm, but the potential energy of that ball has become kinetic energy and it falls to the ground, pulled along by gravity. So potential energy is the potential for energy to become a different form to do work, right? So a membrane potential is a difference in charge between two environments. So we'll see a picture on the next slide. Our example here, of course, is going to be the intracellular versus the extracellular environment. When ions move across the membrane, they're going to change the electrochemical gradient, right? So we can start with our normal gradient, right, with our normal sodium gradient, say 150 millimolar on the outside, 15 on the inside, and we see movement into the cell, but that's going to change the gradient, right? And that change will allow your cells to use their stored energy, that membrane potential, to, enact critical cellular processes. This is the same concept as a battery. One side of your battery is positively charged and the other is more negative. And this creates a potential energy which, when we run a current and connect these two things between the battery, forces ions to move from one side to the other, and then we can utilize that movement, that current, for work. So if you're interested, your book talks a little bit about batteries, but we're actually going to just look at this diagram here. So this is an example of a membrane potential with some ions. We have here two positively charged ions in the middle, so that's 2 plus, and we are not in the middle, in the intracellular space, and we have 1, 2, 3, 4 negatively charged ions in the intracellular space. So 2 plus or minus 4 on the inside of the cell. That is a total charge of -2 just for this section here. And then we have 1, 2, 3, 4 positive ions on the outside of the cell, and we have 1, 2 negative ions on the outside of the cell, so that totals a +2. So that's the charge on the outside versus the charge on the inside. Our extracellular charge is +2 and our intracellular is -2. So this means that there's a difference of 4, right? The numerical difference between -2 and +2 is 4. So here's the thing. Since the membrane potential is always defined relative to the exterior of the cell, we say that this cell, which is more negative on the inside, has a -4 millivolt membrane potential, all right? We say, okay, the inside of the cell is more negative, so we're going to adopt the negative sign. If it were more positive, this would be a positive, right, sign. And then we take the difference in the, more or less, the concentration or the number of charges, right, which ended up as a +2, or sorry, as a +4. And then we say that's in millivolts because it is the potential for electrical energy. So that is how you calculate out, based on this information, right, what the membrane potential is. And again, a negative potential just means that the cell is more negative on the inside than it is on the outside. If this were a positive number, it would be because there were more positive ions on the inside. So we ended up with a positive number. Electrochemical equilibrium occurs when there's no net movement, all right? So we're balanced. How does this work? How is it that we've talked about like concentration gradients before, right? And how when the concentration gradient is equal, we've reached equilibrium, but electrochemical equilibrium is a little bit different. So take sodium, for example. The concentration gradient is going to be pushing sodium into the cell because it's really heavy on the outside and really light on the inside, right? So we have a high concentration on the outside and low concentration on the inside, pushing those ions into the cell. However, positive charges repel other positive charges, and so electrostatic repulsion is shoving those sodium ions back out of the cell. We've got a bunch of positive ions here. These ions are trying to get in, and there's a bunch of positive stuff in this space, so they get booted right back out. And so we have these two opposing forces, the concentration gradient and electrostatic repulsion. The equilibrium, our electrochemical equilibrium, or our equilibrium potential, where there's no net movement of cells, of ions, is a balance of both the inward and the outward forces. So our equilibrium potential depends on the concentration gradient and the charge of any given ion that we're talking about. And so when we reach that point where electrochemical repulsion is not, overcoming the gradient, and the gradient is not overcoming electrochemical repulsion, they're working together, they've reached an equilibrium. That is electrochemical equilibrium. Here we have some common ion equilibrium potentials. So that's here, E ion, that's equilibrium of the ion. So some important notes here. Firstly, if the concentration gradient is 0, so say we had 10 millimolar of chloride on the inside and 10 on the outside, the equilibrium potential is also going to be 0 because, if if everything's the same, right, it's already equal, right? We don't need to move anything. There's no need. The repulsion is going to be equally repelling across the membrane, and there's no concentration gradient to speak of, so we're not going to see an equilibrium potential. Each ion has a differently independently calculated equilibrium potential, so the equilibrium potential of sodium is not going to be the same or affect potassium or chloride, and vice versa. We're not going to see any effect on other ions. They're all independent. And ion concentrations are regularly, in a normal system, regulated by homeostasis, right? So we're going to see a little bit of flux, but generally they're not going to change very much, right? Because we're always regulating these within a given set of parameters. So what these numbers mean, okay, is that at a certain point, which for potassium is negative 89 millivolts, at a certain point, we see no net movement. So at a certain voltage, at a certain difference in charge on one side of the membrane versus the other. So there needs to be a difference of 89 millivolts, all right, with the inside of the cell more negative because it's a negative number in order to reach equilibrium for potassium. Membrane potential, which we talked about earlier, right, and equilibrium potential are not the same, okay? Membrane potential also depends on ion permeability across the membrane. So here we have a little bit of information here. P ion is the permeability of the membrane to that ion. And so the larger this number, the more permeable the membrane will be to it. Potassium is one of the most permeable ions that we have with the number 1 here. Sodium, one of the least permeable with 0.04. And chloride in between, right? Close to halfway. So more permeable than sodium and less than potassium at 0.45. This, by the way, this high permeability of potassium is due to leaky potassium channels, which are always open even when the membrane isn't being actively excited by something. Moving on to what we call the resting membrane potential, all right? This is kind of taking all the information we've talked about so far and consolidating it into one big number, all right? The resting membrane potential is the point at which all ion movement is equal and opposite across the membrane. So we don't have any more ions moving in one direction than the other. They are equal, all right? This is not, however, a point where ions have stopped moving, right? Because of Brownian motion, we see them constantly moving across the membrane. It's just that there's no net movement. And so like this contraption where we have water flowing into a bucket with a spigot, right? This water level is never going to rise because we have equal amounts of water moving into and out of the system, but the water doesn't stop flowing either, right? It's constantly moving, and so our ions are constantly moving. They're just not changing anything as they do. Now, to kind of sum up what all we've talked about, I want you guys to imagine a cell. And these little circles, these are potassium, okay? And there's a lot of potassium, we're going to pretend, in this cell in the intracellular fluid, okay? Inside of the cell, there are also these super large impermeable anions, things like proteins and organelles and stuff like that. So what is potassium going to do, right? Not only is the concentration gradient super high, where we have a bunch in the cell and not much out of the cell, but it is also electrochemically not stable right here because there's a lot of positive charges here, so we're repelling a bunch of ions across the membrane for 2 reasons. And so we see potassium start to diffuse down its concentration gradient and its electrochemical gradient. So at this point, our intracellular fluid becomes more negatively charged. We've lost a whole bunch of positive ions, and these negative charged, like proteins and things, are going to force this inside to be more negative. As the intracellular fluid becomes more negative, it's going to exert attraction for the potassium. Some of it is going to come back into the cell. And at some point, we reach equilibrium, all right? Approximately at negative 89 millivolts, right? And potassium will have no net movement in or out of the cell, so as much that goes out will come in and vice versa. This is a really great way of kind of summing up everything we've talked about. But let's look at another way and look at the actual resting membrane potential and its relationship with equilibrium potentials. So as the permeability of an ion increases, the resting membrane potential moves toward that ion's equilibrium potential, okay? So remember our values here. Potassium and chloride ions were very permeable through the membrane, right? And these are their equilibrium potentials, right? Negative 89 for potassium and negative 66 for chloride. And we can see that our resting membrane potential at negative 70 millivolts, this is kind of the average resting membrane potential that we have, the average voltage at which ions tend not to move, is right in between those, pretty much. And we can also see that as the permeability of an ion decreases, the resting membrane potential moves away from that ion's equilibrium potential. So positive 61 is sodium's equilibrium potential. So this is the charge at which sodium will be in equilibrium around a cell, and our resting voltage, our resting membrane potential is just, it's so far away, all right? Because sodium is super impermeable, right? It doesn't really do very well going through the membrane on its own, and so it doesn't have a lot of an effect. These ions have more of an effect on the resting membrane potential because they are more permeable. Time for another question. If the permeability of sodium were decreased, what would happen to the resting membrane potential? Would it increase? Would it decrease? Would it increase and then decrease? Or would nothing happen? So go ahead and take a couple of seconds and answer this. Pause the video now. Okay, I hope you took a couple of seconds to answer this one. If we decreased the permeability of sodium, which is already super impermeable, the resting membrane potential would decrease. It would get further and further away. Check this out, right? As the ion's permeability decreases, the resting membrane potential is going to move away. Because the equilibrium potential of sodium is a positive number, that means that our resting membrane potential, if this became even less permeable, would be shunted even further into the negative, all right? So the answer here is B. Let's talk just a little bit about neurons. Neurons are excitable cells, just like our muscle cells are. And the job of a neuron is to detect a stimulus and then to transduce it or to change it in form to an electrical signal. So the stimulus could be light, it could be smell or sound, it could be touch, pressure, temperature, it could be any number of things. But a neuron's job is to take that stimulus and to change it, presto changeo, right, into an electrical signal that our brain can understand. So this is a couple of neurons here. We're going to see this diagram a couple of different times with a couple of different labels. We're going to start by labeling what's going on here. Here is our cell body and the axon here. So we start with the body of the cell. This type of cell is particularly called a stellate cell, S-T-E-L-L-A-T-E, meaning star-shaped. And here at the middle of the star, we have our soma, or our cell body, which is going to be full of cytoplasm and organelles and things like that. In the very center, we're looking at the nucleus, but the whole cell body is this whole structure here. The dendrites are these projections that kind of are short but stick out of the soma, or the neurosoma is another word for it. Oh my goodness gracious. Sorry about that, you guys. Anywho, you'd think I'd learn. Anywho, we have the dendrites. Their job is to receive signals from other things. Next, we move on to this kind of hillish structure right here, this kind of mound right here. This is called the axon hillock, and it contains what we call the trigger zone, which is where action potentials or signals are generated, and we'll talk more about that as we move forward. Right here, this long kind of tail-looking situation, this is the axon. And the axon is going to send potentials or action potentials or signals to a target cell. Sometimes it's another neuron, sometimes it's not, right? Sometimes it's a muscle cell like we talked about in chapter 7, chapter 9, whatever chapter it was. Here at the very end, we can see these terminal branches. That's what this branching is called here at the end of the axon. But at the very end, we have this kind of bulbous projection here. This is the axon terminal, which is the site of signal output, just like we saw at the neuromuscular junction. Anytime we have a connection between two cells where a signal is going to be sent, that's called a synapse. Here we can see a synapse right here between this neuron and the next neuron. And this is just a connection, right? And it's how neurons relay messages to one another. So we start with our presynaptic cell. This is the neuron that's located before a synapse. It's going to send a signal down its axon to the postsynaptic cell. The postsynaptic cell is the neuron or the cell, right? It could be a muscle cell or something located after a synapse, and it's going to receive that signal and do something. It could be sending another signal, like this neuron might be here, or it could be actually doing work, like our muscle cells or other effectors. In between, we have that synaptic cleft, like we talked about with the neuromuscular junction. That's that space in between the axon terminal and the target cell, and it is filled with interstitial fluid, or the fluid that resides between cells in a tissue. Time for yet another question. So this question, which part of the neuron transmits the electrical signal from one end of the cell to the other? Is it A, a dendrite, B, a soma, C, an axon, or D, an axon terminal? So go ahead and take a couple of seconds to answer this. Pause the video now. All right, I hope you went and answered this. This kind of question might be a little bit tricky, but let's read it. Which part of the neuron transmits the electrical signal from one end of the cell to the other? So we're not saying, like here, we're talking about this, right? From one end of the cell to the other. This is still the same cell. So the correct answer is C, axon. We talked a little bit about action potentials, signals that are going to be sent down an axon in a neuron. But in order to get to that point, we have to start with a less dramatic situation here. We start with a graded potential. When the neuron is stimulated by chemicals, light, heat, or mechanical forces, that causes a local disturbance in the membrane potential, right? We're going to see channels that are going to be gated, that are opened by one of these stimuli, and it's going to allow sodium to influx and potassium to efflux, right? The response here begins in a dendrite, all right, because we're receiving signals in the dendrites, and they're going to spread through the soma, travel down the axon, and then eventually end in the axon terminal. But we start with a graded potential, all right? A stimulus is going to start a chemical signal. Maybe you have smelled something, right? A chemical is going to bind to a neuron that is located, the soma is located in your nose. And that ligand, that chemical, is going to bind to the receptors on the neuron that are going to open ligand-gated sodium channels in the membrane. Time for another question. Based on what we just said, we've opened up these sodium-gated channels. Which way is sodium going to flow when the ligand-gated sodium channels are opened in the membrane of the neuron? Are they going to flow into the cell, out of the cell, neither direction because they're at equilibrium and there's no ion movement, or in neither direction because sodium is at equilibrium and there is no net ion movement? So which one is correct? Go ahead and take a couple of seconds to answer this and pause the video now. Okay, so the correct answer is into the cell. We know this because on the outside of the cell, right, we have 150 millimolar concentration of sodium, and on the inside it's only 15. And so we have that concentration. It's still going to be the same in this neuron that we're talking about. So influx of sodium is going to cancel some of the internal negative charge of the of the neurosoma. And so the voltage across that membrane is going to drift closer to zero. Remember, we start out with our resting membrane potential of -70. And so when we have, say this is 0 and this is -70, when we have this change, we start seeing drifting upward. At any point, if we have a voltage that shifts from a negative value to a less negative value, right, closer to 0 or closer to a positive number, if we were at 0, right, going up is the same kind of thing, just further away from negative numbers, we call that depolarization. So this is happening, and this is depolarization when we start seeing movement, right, toward 0. That incoming sodium is going to diffuse for really short distances along the inside of the plasma membrane. So if we have the inside of the plasma membrane and we have a bunch of sodium incoming, it's going to move from areas of high concentration right here outward just a little bit to areas of low concentration until we've reached equilibrium in the inside. And it creates a wave of excitation because as sodium moves along the membrane, we're going to see the opening of more voltage-gated ion channels, which are then going to, spread more ions, and then we see the influx of more, just like we saw with propagation of a signal down a muscle cell. There are several characteristics of graded potentials that we want to talk about. The first of these is that when graded potentials occur in dendrites, we call them synaptic potentials. Graded potentials also vary in voltage according to the strength of the stimulus. That's why they're called graded potentials. If the stimulus is very small, you're not going to have much voltage going on, right? A very faint smell is harder to detect and understand and comprehend in your brain than a very concentrated smell. So if you have a strong stimulus, you're going to have a strong graded potential. Graded potentials are also decremental. The signal gets weaker as it spreads from the point of origin. This is partly because sodium is pumped back out of the cell, and partly because as sodium spreads along, depolarizing the membrane, potassium flows out and reverses the effects of the sodium influx. And so we have a super strong signal in the middle and then a weaker signal as you go. Graded potentials are reversible. When the stimulation stops, cations diffusing that were going into the cell are going to diffuse out of the cell very quickly. They're going to repolarize the membrane. And our graded potentials can either be excitatory, depolarizing the membrane, which is what you need in order to generate an action potential eventually, or they can be inhibitory, which are going to hyperpolarize the cell. So since we have to be depolarized in order to send a signal, hyperpolarizing, or making it even more negative, is working actively against that. So here we can see some diagrams. We have, starting with the resting membrane potential on both of these. An excitatory postsynaptic potential, or an APSP, is going to go from -70 to a less negative number, right? That's the direction we're going. We're seeing positively charged ions moving into the cell. However, like maybe sodium, right? We have sodium influxing into the cell, making this more and more and more positive. We could also have an inhibitory postsynaptic potential, or an IPSP, where we start at the resting potential as well, but instead of opening up sodium-gated ion channels, maybe we're opening up chloride ion channels, and we're seeing this becoming more and more and more negative, hyperpolarizing that membrane. And that is going to prevent a signal from being sent, because we need to go, right, more positive in order to send a signal. Another question here. An excitatory postsynaptic potential, or an EPSP, is which of the following? Is it depolarizing, repolarizing, hyperpolarizing, or none of the above? Go ahead and take a couple of seconds to answer this one and pause the video now. All right. An excitatory postsynaptic potential is going to depolarize. We want to depolarize to send that signal, right? If we're going from negative to less negative, that is depolarizing. That's excited. It's excitable, excitatory. So this diagram here, this is looking at summation. So there are a couple of ways in which we can achieve summation of graded potentials. The first of these is called temporal summation. Temporal meaning time. So if we have multiple signals that are going to all occur very frequently, right? That is temporal summation, just like we saw with muscle twitches. So if our stimulus is going to be frequent, we're going to see summation of our graded potentials. We also have spatial summation. No neuron, well, I'm not going to say no neuron. Most neurons don't just have like one axon to one dendrite, right? It doesn't look like just like this. They've got a whole bunch that are all coming in and communicating together. And so our spatial summation means that we're getting signals from multiple axons coming in, right? So having multiple sources of a signal, or having, that's spatial summation, or having several signals from the same axon that are very rapid in pace. So let's actually take a look at what's happening here. The first of these is seeing what happens when there's no summation. So if we have just one graded potential, and then a while later another graded potential. And you can see, just like with our muscle twitches, an individual muscle twitch not going to be able to do work, right? And same here, our individual graded potentials really can't do much. They're too decremental for that. But here we can see that when we see multiple stimuli, increasing the strength of the stimulus, we're going to get our membrane voltage from -70 at resting membrane potential to -50-ish. And so this line here, this number, which is actually -55, it should be, is what we call the threshold potential. Once we reach that value, we're going to generate an action potential, okay? And so this is an action potential, and we'll talk about this in the next video. So this is an action potential that we will see propagating. We can come back down. We have spatial summation. Maybe we have multiple signals coming in from different locations. We're going to see summation of those here as well. They're all happening at once, right? You can have individual ones and then have them all happening at once, and that is going to, of course, depolarize to this threshold potential and go. And we can also see cancellation, right? So say we have an excitatory post-synaptic potential here, where we're going to try and depolarize the cell. But if we have an inhibitory one, that's bringing it even further away from this threshold potential. And we have to reach this threshold potential in order to generate an action potential. Now, if this is confusing, just know that the takeaway from this diagram is not the action potentials or the threshold potential. We will talk about those more later. But the takeaway here is that if you increase the frequency of stimulus, or you increase the number of stimuli that you receive in the same time, you're going to generate a signal. And if you only have singular or weak signals, or if you have inhibitory signals, you are not going to generate a signal. Okay, so this is the end of the first video. The second one should be posted by the time that you are watching this. And we're going to talk about action potentials, what they are, what they do, and how that is important.